So the MEL seminars are back after a long break while we were in Berkeley. And today we're very happy to welcome Malte Helmert, who will tell us about planning. So without further ado, please.
Thank you. So I did budget for 60 minutes. So we will take a little bit longer, given that we started a bit late. I hope that's all right. The topic today is low bound functions for optimal classical planning. And I think for this audience, I need to first explain briefly what classical planning is. I'll do this at a very high level. At the highest level, this is sort of the quote I like a lot from our treasured colleague, Patrick Haslam. Planning is the art and practice of thinking before acting. So we want to do something, want to take actions, and we apply some form of reasoning before we do that. You can make it a little bit more technical. Jörg Hoffmann says, well, we want to select a goal-leading course of action. So again, selecting actions, a sequence of actions that takes us somewhere based on a high-level description of the world. Think of a logic-based representation. One thing that is important, so the audience here will be very familiar with things like SAT solving. Similarly to that, we want a general problem solver. We want domain independence. So we're not interested in algorithms that solve one specific planning problem, but anything that can be represented in, well, within the languages that we support. But it's supposed to be a general problem solver, and that's where the challenge comes from. Here's one example, the 7 bridges of Königsberg, not a very pretty picture, but it's in the public domain. A famous unsolvable planning problem where the task is to basically do an Euler path or an Euler tour of the city of Königsberg, that is, cross each of these bridges exactly once. So that's something that doesn't have a solution, not too hard to figure out with some kind of exhaustive search, because it turns out there's only about 30-ish reachable configurations of this problem, which would be defined in terms of where we currently are, which bridges we already use. And of course, we all know that there's a very neat, nice mathematical criterion that Euler came up with, thus more or less founding graph theory for deciding which instances of this problem are solvable and which ones are not. Similar problems arise in lots of applications. So here's a picture sort of showing a space probe. So people that work in the aerospace industry, particularly in space, are very interested in planning because they want a high degree of autonomy, sort of resistance tolerance to system failures, partial system failures. So they want to figure out how they can reach their scientific goal, their mission objectives based on changing circumstances. Another example that we were a little bit involved in on an application side very slightly is an intelligent greenhouse, where you have to shuffle plants around on conveyor belts in order to take various measurements. And maybe sort of easier to formalize are abstract problems. So here you see a solitaire card game with full information. This is the free cell problem that comes with Microsoft Windows. So in a game like this, you have full information. There's also solitaire games with hidden cards. That's not classical planning. That's a more general flavor of planning. But here we have full information, and in principle, we can reason our way towards the solution, figure out all the actions we need to take in order to win this game before we ever move a card, right? Because it's all perfectly predictable what's going to happen. And all these are standard benchmarks that are used in the planning community to evaluate planning systems. So we can think of it as a kind of graph search. So we want to go from the state on the left with the incoming arrow that comes from nowhere to any of the green states. Those are the goal states, which means finding a path on the graph. The problem is, the reason why we don't just apply Dijkstra's algorithm or something like that is because the graphs are large. Just like in SAT, we have small inputs that represent a large space of configurations. So here are some typical problem sizes, maybe a bit less impressive to people known to SAT, but of course the problem is more challenging in the sense that we have to find an entire sequence of configurations, not just a single configuration. So we're really happy if we can scale it to problems with, let's say, 10 to the 100, 10 to the 206. So the most prominent technique, and of course, like Jakob said already, if at any point you have a question, please interrupt. Otherwise, yeah, we may lose you. But so the most popular technique, there's essentially 3 main algorithmic paradigms for solving classical planning problems. And the most common one among those is called planning as heuristic search. So it's based on using a general search algorithm. Most people would be familiar with something like A*. If not, it doesn't really matter for this talk. And what is, well, a distance estimator, or what in the planning community or heuristic search community is known as a heuristic function or heuristic. And I added a little nota bene there, mind the terminology gap. So heuristic is a word that is used with sort of many different, sometimes fuzzy meanings in different parts of computer science. When people talk about heuristic in this context, they mean something very specific. namely a distance estimator. So what that is a function that takes the state of the problem, so one of these nodes, and spits out a number that estimates how far away we are from the goal. So for example, if I assume I didn't put edge weights here, normally we also have costs, but if all these edges are unit cost, then the shortest path from the initial state to the green zone would take 4 steps, like the one I showed is one of the possible optimal ones. So ideally, I'd like my distance estimate for that state to be close to 4, because then I have good information about how valuable this state is in a sense. We are especially interested in algorithms, and for the purpose of this talk, only interested in algorithms that find optimal solutions, so shortest paths in this graph. And for this, you can't just take any distance estimator, you need some guarantees, otherwise you never really know which states you can rule out and which ones you can't. And the common requirement that all the algorithms have, there's some sort of details to that I don't want to go into, is that our heuristics or distance estimators give us lower bounds. So if I give a value of 3 for the initial state, that's fine, because the truth is 4. If I give 10, that would not be okay. So the algorithms people use would lose the optimality guarantee if you don't have a lower bound. Now you can use a trivial lower bound. You can use 0, for example, 0 for every state. If you do that, A star is simply Dijkstra's algorithm. So any way you improve your bound, well, the algorithm becomes better, basically. There's a second condition I'll talk about a little bit later called consistency. It's a form of triangle inequality. It's a little bit less important, but still reasonably important. So one way to maybe explain why it matters is that you can think of A star as doing Dijkstra with modified edge weights. And if your heuristic is consistent, then your edge weights stay non-negative. If heuristic is inconsistent, you can have negative edges in the graph, which you can modify the excess algorithm to deal with that, but it's a bit nasty and it costs you efficiency. So ideally, you'd also like this consistency condition. It's a very old approach to planning, more than 50 years old, and the most successful one. I'm saying one of the most successful ones, but it's certainly the one that is getting the most attention.
But just to be clear, again, this terminology things, when you talk about the heuristic,
yes,
this is actually something with some kind of rigorous guarantees. So it's not like a set heuristic in the sense that it might work well, but we have no idea. Your heuristic will typically, the lower bound will be true.
So a heuristic is any distance estimate. So it's any mathematical object that maps the state to a number or infinity. If I have this guarantee, I would call it an admissible heuristic. So an admissible heuristic is such a function that is guaranteed to be a lower bound on the true cost. Make sense? Okay. Now, of course, like I said, if we use a trivial heuristic, we just get that Dijkstra's algorithm. That's not going to scale to 10 to the 200 states or something like that. So whether these algorithms work or don't in practice depends on how good our heuristics are. So the question is, how do we come up with good ones? And how do we do that? Well, based just on some of logic-like specification of a problem, right? Not being able to bring to bear our own intuitions about these problems. So for a long time, this was considered something of a dark art, or like a little bit of magic, not something incredibly scientific. Just try to think of something, okay, it works, okay, it doesn't work. Try to think of something else. That has changed a little bit over the last 10, 15 years, say, where really I would say a large part of the exciting, or what I find most exciting research in the planning community is in developing a kind of science of heuristics, like trying to understand their relationships, sort of positive and negative results, like certain classes of heuristics, what can and cannot they do, these kinds of things. And that's what in our research group we're primarily working on for quite some time. So that's sort of the goal. And today I want to talk about what I would call a declarative view of these distance estimators of these heuristics. Hopefully it will become clear what I mean by that. But it's declarative, I mean, as opposed to black box. Like traditionally, the view of a heuristic is a black box. You have a function, you plug a state in, you get something back, and you don't get to look inside. This is problematic for various things, but one reason why it's problematic is usually, well, there's often you want to use more than one heuristic. You want to use 2 or 3. And if you have 2 or 3, or more than that, if you have 2 or 3 black boxes, you don't really have a good way of combining the information they give you. What you can do if they're lower bounds is to take the maximum, but you can't really justifiably do anything better than that, anything else, combine them in a less trivial way. And that's why I want to open the box a little bit, look at heuristics in a slightly different way. and to have the computer do a bit more reasoning about the problem. And well, there's three things I want to talk about, three topics that in a sense build on each other. So this is in a way like one stream of research, a continuous line of research. Three parts. The first part will be on cost partitioning. The second part is on operator counting constraints. And the third part is on potential heuristics. I hope we'll be able to finish all of them in the allocated time. And all of them is about like how can our computer help us come up with a better heuristic. The first part is exactly about the thing I just talked about, combining multiple heuristics. That's what cost partitioning wants to do. So basically what our computer is asking us, you seem to be struggling with a large number of distance estimators there. Would you like me to combine them for you? Is there a principled way we can do that? And I'll talk about the other two more when we get there. So cost partitioning. I'm going to use this as the running example. This is also one of the original benchmarks that you'll find in the literature. So for example, the first paper on IDA star, like an algorithm that improves on A star in terms of memory usage, Richard Korf, very famous, used this problem as a benchmark that it wanted to solve optimally. So this is the sliding tile puzzle, 4x4 puzzle or 15 puzzle. Let me just ask in the room, who's familiar with this problem? Who knows how it works? Not everyone, okay. So what you have here is the physical puzzle with 15 tiles and one empty location. And the actions that we can take is slide a tile into the empty location. So for example, you could slide the one to the left, that opens up a space where the one was, you can slide the 14 down and so on. And at the end, we want to get to this configuration on the, well, we start from a randomly shuffled configuration. We want to end up with a sorted configuration. It's a problem that is easy enough to solve if we're not interested in optimal solutions. If you want to solve it optimally, the generalized version of this, like an n-by-n puzzle, is NP complete. It's not worse than that. Planning in general is p-space complete. So this is not as hard as a general class of benchmarks can get, but it is pretty hard. And yeah, no, that's really kind of all we need to know about the problem at the moment, I think. And okay, you can imagine that I can easily encode the rules of this in a sort of logic-based representation, which would talk about fluence like a location is in a particular position, a particular tile is at a particular position, so it could have 16 times 16 of those. That particular location is unoccupied, and then come up with some sort of way of describing how I can transition from one configuration to another following the rules of the game. And I'm not going to talk about these languages here, but maybe in the second part. So what I want to do now is trace the ideas that people had for distance estimators for this specific problem, and sort of try from that to draw out something a little bit more general, and in particular, tease out this idea of combining multiple different estimates in a principled way. And these ideas are called Manhattan distance, linear conflicts, pattern databases, and additive pattern databases. So like I said, the key challenge that we're going to be interested in is how do we combine many lower bounds into one lower bound? So the best known heuristic that you also find in many AI textbooks, it's not even very bad, but it can be improved, is what is called the Manhattan distance. So what you do is for each of the 15 tiles, you count how many steps does this tile have to move at minimum. So for example, for tile number 1, from where it currently is, it has to go up twice and left twice. That's sort of the shortest way to get where it needs to be. So that contributes 4 to the heuristic value. And you do that for tile number 1, for tile number 2, 3, 4, and so on for all 15 tiles, not for the blank tile. That way you could get overcounting. And if you do that in this case, you end up with a number 42, which I didn't choose as a meme, it just happened randomly. So this is the Manhattan distance heuristic. And it is a lower bound because in a way it only counts things that you really also have to do in the real solution. I'm not being very precise. That's not enough of a proof. But I hope it's reasonably, okay, basically in the best case, every real move you take can reduce this Manhattan distance of at most 1 tile by at most 1. So every move you take can lower your heuristic by at most 1. And that's enough for this to be a lower bound. Yes, there's a question.
Not perhaps while you move those, so suppose you're doing this potential function argument, but as you're moving 1, somehow 2 is also, you're making progress on 2.
Right, well, that can't happen. And that's important. No, but that's important. That's precisely the reason why, for example, I don't count the distance of the blank.
Yeah.
Because definitely the blank can change its location at the same time as the tile I'm moving. So that's precisely the reason why I'm not doing that. And indeed, this point will become also relevant for the sort of fourth heuristic we're going to talk about, the additive pattern databases. So that's a very important point. Okay, so the first improvement to this was described was an idea called linear conflicts. So the observation there was sometimes if the tiles move to where they need to be on the shortest path, they necessarily clash with each other. They get in each other's way. So we start from an Manhattan distance, and then we look for tiles that clash. So here, for example, the 5 on its shortest path would have to go directly to the left. The 7 on its shortest path would have to go to the right twice. And you can see that you won't be able to do this with a minimal number of moves because, well, I mean, hopefully it's clear enough. If not, I guess you believe me. So basically, one of them will have to make room for the other one at one point. So either the 5 or the 7, in the best case, gets out of position once, essentially going up or down. And then this is a move in the wrong direction, so you'll have to undo it. At a later point, it will have to, well, if it went up, it will have to go down again. So for one of the tiles, 5 or 7, you definitely need at least 2 extra moves. So that's the idea of linear conflicts. You identify pairs of tiles that get in each other's way. And for each conflict, you add +2 estimates for each conflict. And now we're actually, again, at the point of that question, you have to be a little bit careful about this because like a single, what's the word I'm looking for? Like a single avoiding move, a single detour can contribute to improving multiple conflicts at the same time. So you have to be careful if these conflicting pairs overlap in some way. I don't want to talk in detail about what's the best way to do it. You can do some kind of vertex cover or something on a graph, but that's not the point here. The point is we now have an idea for dealing with, in some sense, 2 tiles at a time. But as soon as we do that, we have to be very careful about the interactions between overlapping pairs. In this example, this is not a problem because this is the only conflict. So we can take it into account, improve the heuristic value by 2, get it to 44. And of course, because there's a lower bounds by improve, I always mean get a higher value, right? We always prefer the higher values because they're closer to the truth. So maybe it's not even true, the first bullet point here. I'm saying so far it's hard to see much of a general picture, but I already indicated maybe there is something general we're moving towards, this idea of looking at like one aspect of a problem at a time or 2 aspects of the problem at the same time and trying to do something with that. So with Manhattan distance, we focused on only one tile with these linear conflicts. We're now looking at 2 tiles at once. And this seems to be something we should be able to generalize. But also, we already have this complication that we get that, well, if we have multiple conflicts involving the same tiles, we have to be really careful to guarantee that we still have a lower bound. Okay, so the natural progression is, let's not look at 2 tiles, let's look at an arbitrary set of tiles. And this is a very influential technique called pattern databases, influenced by endgame databases in 2-player games. So Jonathan Schaefer, the second author here, is famous for writing a system, implementing an algorithm that solves the game of checkers in the sense of playing it perfectly, so it will never lose. And with perfect play, that game's a draw. And the key technique there was so-called endgame databases. Like you solve the game if there's few pieces left on the board. And they try to adapt this idea in some way to these single-player games, if you want to call them that, to these search problems. And that was what they came up with. So the idea is you pick a subset of your tiles, you call that the pattern, and you treat all other tiles as if they were the same. So let me do that. The subset I'm picking here is what is often called the fringe. So the tiles that have to be at the end, at the top or at the left. So that's the numbers 1, 2, 3, 4, 5, 9, 13. So if I'm sort of physically rubbing out all the other numbers and solve the resulting puzzle, I'm making the problem easier, right? Because previously I had to get everything in place. Now I have to get only 7 of them and the blank in place, and the other ones I can permute a little. So if I solve this easier problem optimally, well, the cost of that is a lower bound for the real problem. Hopefully that makes sense. I essentially, one way of looking at this is I, in some sense, kept the rules of the game the same, but I enriched my goal set. Now I'm not looking for one specific configuration, but only all the configurations that work for these tiles in the back. And well, the idea is to throw away or discard enough information about the problem that the resulting problem can be solved by brute force. So in this case, I have well, 7 tiles left to worry about, plus the blank. So that would give me 16 times 15 times 14 and so on, all the way down to 9 possible states, if I did the calculation correctly. And that is something I can fit into like a gigabyte of RAM or something like that. Like that, all the distances, all the goal distances for this problem. And the idea is, for the simplified problem, you compute all the goal distances in one pre-computation with a single Dijkstra algorithm that goes backwards from the goal. So you get all the distances to the goal, and after the pre-computation, you use that as a heuristic. Now, that looks very much like a general idea. So if I have some kind of logic-based representation, all I have to do is say, well, let's focus on a subset of my variables, subset of my logic variables. Here we often use finite domain variables, and somehow make sure to get rid of the distinctions for the other ones. If you're thinking about logic, you can think of some kind of free-valued logic for those or something like that. Depending on the representations, there can be syntactic ways of projecting them away in a way that is an over-approximation. I don't want to go too much into the detail, but the idea is essentially to project those away, make the resulting problem small enough. We can do that for any type of problem. Now, the issue is that in an interesting problem with one pattern, we're only going to capture a small fraction of the problem. Like if I have here, we're sort of capturing half of the problem, but this is because this isn't a large problem. If I have, I don't know, 10 to the 100 states, and I have to get this down to something I can fit into main memory, like 10 to the 9, what it means, I'm really only looking at a small fraction of the problem, and therefore my estimates are not going to be very accurate. At some point, this stops scaling. Oh, well, it stops scaling well. And of course, the obvious solution is to use more than one pattern. And now we could easily, and this was done from the start in pattern databases, we could just use 2 or 3 or 4 different patterns and maximize over them, maximize over the estimates. But it doesn't really solve the problem in the sense that each individual number I get will be from one of these heuristics ultimately. So each individual number will only be based on a small subproblem. In some sense, it will select the hardest subproblem among the ones I'm considering, but nevertheless, each of the estimates will be only looking at a small subproblem. And again, this tends not to give very good estimates. So what I want to do is I want to take multiple projections, multiple patterns, and somehow add up their values. If I do that, I get the same problem we got before, namely that I'm essentially counting the same things I need to do multiple times. Now, if there's something that makes progress in sort of 3 abstractions at the same time, that can factor into all the 3 heuristic values I'm getting. So if I'm adding them all up, I'm counting 3 where I should only count 1. So how do we deal with that? Well, the original idea in this last heuristic I want to talk about, additive pattern databases. Again, Richard Torf was involved in this, who also came up with AEA star, and Ariel Fellner, a very, very influential idea, is to pick several subsets of tiles and make them disjoint. So partition the tiles, essentially. You usually want to use every tile in some pattern. Now you get these subproblems, and you solve them like you do with regular pattern databases, but in a slightly different way. Namely, in your simplified problem, you're only counting the moves that actually change a tile in the pattern. What do I mean by this? Maybe let's go back here. On the left, okay, this is not the best example. So I have 4 possible moves, and each of these will change a tile in the pattern. They will move tile 3, 5, 1, or 4. If I look at the goal state, well, the only moves I take only change the position of the blank. That doesn't count as a tile, and I don't want to count it as a tile for reasons that hopefully, well, I do want to count this move here in the single pattern databases, but in the additive pattern databases, I don't count these moves anymore. So I'm in the additive pattern database world. I'm again solving this problem, but all the moves that only exchange the blank with a star, they are now free. Okay, everything else still counts, but those are free. Why do I do that? Because that guarantees that every move I make in the real solution can only make progress in one of the abstractions at the same time, because it only moves one tile, and the different abstractions use different tiles, and only the movement of the tiles count. And yeah, every move only moves one tile in particular. I think I said that multiple times. Okay, so that's the idea. Solve the induced subproblems as with regular pattern databases, but only count the cost of moving the pattern tiles. And then the sum of these estimates will be an admissible heuristic. Now I'm asking the question here, how is this related to Manhattan distance? let me answer it myself straight away. Manhattan distance is actually the special case of this, where I use 15 minimal abstractions of only one tile. So this is in some sense a proper generalization. More generally, if you take any partition and in some way, like you combine things into larger equivalence classes, like now I'm combining 1 and 2, the heuristic can only get better, can only get more accurate. But of course, as I take larger and larger subproblems, I increase my memory requirements, my computational costs. So this is the trade-off. So here's an example where I partition into 2 groups, a blue group and a red group. And then I can come up with the estimates and add them up, but I didn't do the math here. So at the time this was sort of conceived and then implemented and tried out, it worked more than 1,000 times faster than previous state of the art. And this is really a problem which is very much like a race. Like these were not people dealing heavily in theory. They wanted to solve these problems as efficiently as possible, and that's all they cared about. Can I solve this problem or not? And anything goes, including computing for 4 months. So this was really a breakthrough in terms of scalability. And in particular, it also allowed us for the first time to optimally solve the 24 puzzles, so the 5x5 puzzle with one bank. However, at the time, and maybe this doesn't make sense the way I'm presenting this, but you have to bear in mind that these techniques were very much invented in the concept of this puzzle, describing things in terms of these puzzles, not sort of at a higher level. So at the time, there was this comment by a famous member in the research community saying, okay, neat idea, but it's not going to work for anything other than the sliding tiles. Because it relies on certain aspects that you only have in this puzzle, in particular, this idea that a move only affects one tile at a time. So one reaction was, neat idea, won't generalize. And so that's sort of the one aspect. And also like this thing where we say, well, let's not count the moves of the pattern, let's only count the moves of the pattern tiles, not the other moves in the abstraction. It sounds maybe a little bit like a hack. It sounds like something that we have to come up with to make it work, but how principled is this idea? Can we distill something for a general problem solver from that? And the idea is, yes, we can. And I'm sort of jumping ahead a few years. There were things that happened in between. I'll show you the timeline in a second. But this is the core idea in its final incarnation, and it applies not just to planning. So it's called cost partitioning. This is not a formal definition, but it's not very far away from a formal definition. So if we have some kind of minimization problem, in this case classical planning, where we want to minimize the plan cost, the total cost of the actions in the sequence, where the solutions are evaluated with regard to an additive cost function. So my solution costs are the sums of the costs of all the actions I'm using. Then what I can always do is split up my cost function, so I can come up with n new cost functions, such that, well, if I add them all together, I'm not using more cost than I actually have. So C1 plus C2 plus Dn is less or equal to C. So if I do that, then I can independently compute lower bounds for, well, n copies of the problem, where the ith copy uses the ith cost function. So in the simplest case, for example, I do what is called a 0-1 cost partitioning over 2 with 2 components. So I basically I split the different actions I have into 2 halves. And in one copy of the problem, I only account for the cost of one half of the actions. And the other problem, I only account for the cost of the other half of the action. And you see that this is what is actually going on in the sliding tile. Like in the copy of the problem where I'm looking at pattern tiles 4, 5, 7, well, the actions that move pattern tiles 4, 5, and 7 count. But in order to satisfy this cost partitioning constraint, I then have to make them free in all the other points. But the general definition is much more permissive. Like I can make it cost 1/2 here, 1/4 here, and 1/4 here, and that would also be fine. I can even, and this is something we only figured out many years later, have negative costs in some of the copies. Like I can set the cost to -1 in one copy, and then I can use 2 in another one, because that will add up to less than 1, and that's all I need. Okay, so I create these different copies of the problem. For each copy, I independently compute the lower bound, then I add up the lower bounds, and this is always going to be a lower bound for my real problem. And so in some sense, I'm allowing myself to optimize for different solutions depending on the cost function. And then, well, add them together. Okay, I think to be more precise, I think I have to be a bit more precise with the definitions. Does it sort of make sense? Okay, so it took quite a while to get there. So what I want to show you, and I don't really want to explain like all the details of this or how it matters, but I want to sort of show how this idea evolved over time. So before this definition, well, we have the paper that I talked about by Korf and Fellner that introduced these pattern databases for the sliding tail puzzle. This one generalized to arbitrary planning problems by Edelkamp, who also came up with what I call an opportunistic additivity criterion, which basically said, well, in some cases, we're just able to add up the cost of two patterns just due to we're always using the original cost function, but somehow, in some cases, it just happens that an action can't make progress in multiple projections at the same time, and then they're what we would call opportunistically additive. And this paper, so the ICAPS is sort of the core A* conference in the area of planning. And so it has this test of time award, where a paper can get an award like 10 years later for being really influential. So this was one of the papers that got this award 11 years later, because it was hugely influential. Not so much for this additivity criterion, more for taking pattern databases to this domain-independent world. Then later on, Hassam and others realized, okay, the thing you're doing that works for any heuristic, not just for the pattern database heuristics you're using. And this was later refined to something called the canonical heuristic function. We called it the canonical heuristic function because in a way we thought this is the best thing you can do. Under certain assumptions, it is the best thing you can do, but you can change the assumptions. And this was the state of the art until cost partitioning really came around, and it dominates Edelkamp's additivity criterion. Dominate always means I get at least the same value, possibly higher, so greater or equal. Then came cost partitioning. Introduced in 2007, cost partitioning dominates the canonical heuristic function. But I'm doing something potentially nasty. I'm saying, well, you have to come up with these cost functions. So this is an infinite space, right? I'm creating n different copies, and for each of the actions of my problem, each of the things I can do, I have to distribute. It's even a continuous problem, right? I can say I'm giving a cost of 0.3 here, 0.6 here, 0.1 here. So are we just saying, well, you have to come up with a good algorithm for coming up with these costs? So the nice idea in this paper by Katz and Domshlak from 2008 was that they showed that for heuristics that are based on abstraction, on homomorphism, don't want to talk more formally about what this is, but the pattern database is an example of this. You can actually, in polynomial time, for a given set of abstractions, polynomial time in the size of the subproblems state spaces, compute the best possible cost partition. So the best possible way of distributing costs among your various problems to maximize heuristic value. So you can solve this optimization problem of coming up with the best distribution of costs among your copies in a polynomial time computation. And this is via linear programming. In a way, you're solving the shortest path problems for each copy in a kind of symbolic way, where you leave the actual costs of all the actions open as variables that you don't fix primarily initially. And this gives you linear programming representation of the shortest path. And then you basically add this constraint here that now you get to allocate the cost between the different subproblems, but only in a way that you're not using up more than you have as an additional linear constraint. And then you take that and find the best possible assignment to your costs, the one that gives you the highest heuristic value. So this is in principle a linear well, it is a linear program, it's polynomial time. The issue is it has like billions of constraints and variables, polynomial but too large, right? This is the thing that exists in practice, right? And nevertheless, hugely important. Actually, this is why I included this ICAPS influential paper awards on these slides, because this paper, very, very rightfully for me, this is maybe one of the three most important papers in planning in the last 20 years, is getting the influential paper award this year, finally, after 15 years. It was announced something like last week, so pretty recently. Okay, and that spurred a host of practical techniques, including something that we did that also got the ICAPS influential paper award. But that would be a nice topic for another talk. But basically what happens here is various ways of coming up with more practical algorithms that don't do the optimal cost partitioning, but still do some form of cost partitioning in a more efficient way and really boost the state of the art. In particular, the second paper here, post-hoc optimization, is a proper generalization of the earlier work on additive pattern databases that replaced an NP-complete subproblem that they had with a polynomial time problem, while actually making the result better. So the insight there was, if you looked at what they did in the right way, you could think of it as an integer problem, but you might as well solve it as a linear problem because there's no reason to have an integrality constraint. And the way that well, the optimization function works in this case is that it's actually to your benefit because you want to maximize. And in linear problem, yeah, I can maximize to higher values and make it a more efficient computation. And other stuff, ultimately, this led to lots of nice connections to mathematical programming. So one insight we saw is that using duality on these cost partitioning linear programs, we can come up with something different that I'm going to talk about in the second part. And this sort of spurred a sequence of papers that try to take these linear programs, understand what they do, and apply various techniques to mathematical optimization and see what they can do in planning. In particular, we now have optimal cost partitioning approaches that are a form of Lagrangian decomposition, and most recently, another form of optimal cost partitioning. That is a form of Bendis decomposition and Danzig-Wolff decomposition. So these all attempt to get as close as possible to the best cost partitioning while being sort of reasonable in terms of the computations they do. And the last two in particular are anytime approaches where you get a better and better cost partitioning over time. You can stop at any time and say, okay, I spent enough time on this. Let's now use this heuristic for such. Okay, so this was the first and largest part. Second part of the story is what I call operator counting constraints. So here we kind of want to, so this idea of information about problems is given in the form of distance estimates. This is the paradigm that was sort of held sacred for 40, 50 years. So this is how intelligent search algorithms work. They work with distance estimates. The idea here is let's not do that. Don't talk to me about distance estimates. Talk to me about what you know about the solutions. So let me try to make this a bit more precise. And let me skip over this actually. So on it, okay, let me not, okay, sorry. Now, one issue with cost partitioning is that I still need a lot of insights to come up with the algorithm that does the actual cost partition. So if I have like 5 different heuristics, I want to do the best possible cost partitioning for them. I have to look into how are these heuristics computed, and can I somehow come up with something like Katz and Domshlak did, sort of express the computation in a linear program or something like that, that I can then link without the linear programs in order to do the global optimization that this would suppose. So I have to study the different heuristic ideas myself in order to figure out how I can do the cost partitioning between. And it would be nice if I had like a general way to do that. If I had something where if I come up with a new heuristic tomorrow, I somehow express it in a way that I can immediately throw it to the pool of existing other approaches and combine it with them in some interesting way. And the idea is that we want rather than having these distance estimators, we want to have something in some sense more declarative, something that tells us a bit more precisely why it thinks we have to do a certain amount of work to get to the goal. And the paradigm here is that rather than getting distance estimates, we get constraints about the set of possible solutions, constraints on the set of feasible plans. And then if I have 10 different sources for these constraints, I can just throw them together and do global constraint optimization. And if I use like a common constraint language for this, then I only have to do this computational part once. Someone's already done it for me. All I need to do is come up with a way to produce these constraints. And of course, this only makes sense if I can come up with a tractable constraint optimization language, and I can express the information I want to express nicely in this language. So this is what we're going to do. And in particular, we're going to use linear programs. So what's the idea? Operator counting constraints. Operator is a fancy word which just means action. So like move a tile up or down or something like that, move a particular tile up or down. It's something that is part of the formal representation and skipping. So for each of these actions, operators, I'm introducing a variable variable x, and that variable counts how often in some solution I'm thinking about I'm applying this action. So if this variable is 5, what it means I'm thinking of a solution where I'm applying this action 5 times. So how often does this action occur in a given solution? One way, and there's different ways of splitting up the things you can do in a problem into such actions here. What I'm doing is I'm saying, well, the level of granularity is I have a different action for every tile in every direction I'm moving the tile. So for example, U1 counts how often tile 1 is moved up. R7 counts how often tile 7 is moved to the right. Now, if the semantics of these numbers is how often I'm doing this in a particular solution, then, well, the cost of the solution is, well, the sum of these variables weighted by the cost of these actions. So if all the actions have a cost of 1, like here, it's just the sum over these variables, right? If I have to do this one 3 times, this one 4 times, and have to do nothing else, well, then the cost is going to be 7, the unit cost. So for example, in the 15 puzzle, I want to minimize this expression. Okay, I know these variables are all non-negative. I'm not going to move a tile to the left minus 5 times. I can think of them as integer variables because they are. Often we use fractional variables instead to make it efficient. But you can use this as an IP or LP computation. And now the question is, well, okay, if I have no information, this will give me 0, right? Set everything to 0, that minimizes this expression. But now I'm adding information. I somehow know I'm going to need this action a certain number of times. And the funny thing, or the nice thing, is that we can easily encapsulate all the information from the heuristics I talked about in this sentence. Yeah.
Arriving at the optimal solution, saying that the number 1 has to be tile 1.
If I know what the optimal solution is, I could certainly do that. What we're going to do is write down constraints that we know must necessarily be true for every solution.
Sure.
But I mean, the more information I have, yeah. Does that answer the question, kind of? Okay. Okay, so let's go through our 4 approaches. Manhattan distance. What I said is that, like for tile number 1, it has to be moved up at least twice. It has to be moved to the left at least twice. I can directly import this with these very trivial linear constraints. U1 has to be at least 2. L1 has to be at least 2. This is going to be true in every solution, so I can post it as a constraint, right? Whatever the optimal solution is, I don't know it, it will satisfy this inequality. Makes sense, hopefully? Well, once I have this insight, I can try to be a little bit more smart and say, well, yeah, okay, I have to move it at least up at least twice. But I know a little bit more. I have to move it up exactly twice more than I'm moving it down. So this constraint implies this one because I know that D1 is greater or equal to 0. And if I know nothing else, they give me the same information. The cheapest way of making them true is to make U1 2 and making D1 0. But maybe I know from another source that D1 is at least 3. And now all of a sudden, these 2 sources of information talk to each other, right? Because this one now tells me, okay, well, given that, U1 has to be 5, right? If I know I have to go down 3 times, well, then I have to go up 5 times because I have to end up 2 positions higher than I started from. So by talking about these properties of solutions, I can express things, I can express sort of interactions in a quite more precise way than what I started with. And indeed, this whole kind of balancing equations is another example of a heuristic that has been used in generalized planning, classical planning in general, which is known flow constraints or network flow constraints, that has been sort of invented independently. Okay, similarly, with linear conflicts, rather than saying, sometimes this can add 2, I can express precisely what I know. What do I know? Well, if 5 and 7 are in conflict, one of them has to move out of the way. So either 5 goes up once or down once, well, at least once, or 7 goes up or down at least once. There's no other way to resolve this thing. This is unconditionally true in this problem. Now, I don't have to worry about how does this interact with information about other conflicts and things like that, right? The constraint solver will do that for me. And if I solve this as an integer program, okay, this by itself is not going to add 2, right? It's only going to add 1. But I also have the flow constraint that tells me, well, if one of them goes up, it also has to go down because the difference has to be 0 in the same line. So I get this for free. I don't get it for free in the linear program, right? In the relaxation, maybe I lose a little bit there. but nevertheless, the information I have is captured nicely. And to emphasize this point, any constraint I can think of, I can combine with any other constraint I can think of, and everything will sort of magically be combined in a way that I'm using all the information available in the best possible way. So in the planning literature, this would be called a landmark constraint, a constraint that says among a certain set of actions, one of them you have to do. This is called a landmark, very influential idea. And again, the overlap here is handled automatically. Okay, and finally, for the pattern databases, let's say in this example, the distance, so this is the additive pattern databases, the distance in the problem for the blue variables is 27, the distance in the problem for the red variables is 20. I can add, well, I could add this up, get 47, but I can also combine this with other constraints in this operator counting world by expressing what I know. Now I'm using auxiliary variables here, I'm just doing that to make the notation a little bit more compact. You don't have to do that, you can expand it. So M1 means movements of one. These are all the possible movements of one, down, left, up, right. And then, well, what the first heuristic tells me is the total number of movements of tiles 1 through 8 will have to be at least 27. And what the second heuristic tells me is that from the red subproblem, the movements of tiles 9 through 15, these variables have to add up to at least 20. And again, I can now combine this. Well, here it's very clear that the sum of these is actually an objective function, the sum of M1 through M15. So it's clear that this gives me a lower bound of 47. But if I express it in this way, I can apply this to all kinds of overlapping patterns as well automatically, and it will take care of it. Basically, distribute things in the best possible way. And again, this turns out to be a way to precisely capture what happened in a paper that was done prior to this work in operator counting constraint, something called post-hoc optimization. Okay, so what have we achieved? We have a uniform declarative representation of heuristic information. It is not quite universal. There are some heuristics, but we don't really know how to sort of convert them into operator counting constraints in a non-trivial way. You can always do it in a trivial way by saying, well, if my heuristic value is 15, then the sum of all the variables will be at least 15, but then this won't propagate with any other constraints. This will make sure your final result is at least 15, but won't do more. For some heuristics, we don't really have a better way than this trivial way, but for let's say 80–90%, there's really nice ways of doing this. And we can easily combine them with each other with maybe also additional problem constraints that might come from the outside. And the actual hard implementation is done by science that solves these linear problems or integer problems. But there's something nicer about this, and that is that we can actually prove that there is a very close relationship between this and cost partition. So if we have n distance estimators that we can, whose information we can describe by sets of constraints of this form, like adjusted in the examples, so 1 through Cn, then if I use all these constraints, pull them together, solve the constraint optimization problem, I always get exactly the same value that I would get if I did the best possible cost partitioning over these n heuristics. And the nice thing about this is, like I said before, for cost partitioning, we didn't have a general way to do it. We have to do it for every heuristic separately. Now we know how to do it. We just express it as a constraint and then run with it. And indeed, when we came up with this, well, we didn't actually quite have this equality. At that time, when people defined cost partitioning, they said, well, split your non-negative cost function into n non-negative cost functions. And what we got out of the LP theory here was something that looked at some point with duality, additional variables, and so on, amazingly like the cost partitioning LP. Instead, we were missing the constraints that said, well, the costs have to be non-negative. They were not there. We kind of wondered, okay, why this difference? And only then we realized, yeah, there's no reason for the costs to be actually non-negative. It's perfectly fine to say in this copy it will have cost of -2, and then you can make it a cost of 3 somewhere else. And well, if the LP doesn't tell you, you don't think of it, or at least people didn't think of it for like the 7 or 8 years that lay in between these two papers. So these are actually the same, but they're only the same because we generalized cost partitioning to also allow these negative. Okay, 10 more minutes. Okay, last topic, potential heuristics. So what we did so far was we took some ideas for heuristics, encoded them as linear programs in a way, and then got the computer to combine them. Now we want to be a bit more radical and have the computer design the whole heuristic for us. So what's the idea? I'm now saying, okay, I want you, computer, to come up with a lower bound function. Please give me one that is as good as possible, which means the heuristic value should be as high as possible, but it nevertheless has to be lower bound. I also want this triangle inequality. And all I'm going to, yes.
So I don't know if this question makes sense, but just when you're expressing things as a linear program,
yes.
I guess in the constraints you had, they were actually integers also.
Yes.
Like, would it buy you anything to say, this is actually an integer
Yes.
linear program, not just a linear
Yes.
program?
Yes.
Although you lose polynomiality, I guess.
Yes. I mean, the short answer is yes. In practice, we do solve them as linear programs. We do solve them as integer programs to sort of test what the result would be. But in the examples we've looked at, the values are usually not much higher than the linear program values. The cost is often higher, so it doesn't seem to pay off with any regularity. But we're kind of looking into changing this from an approach that derives heuristics to an approach that actually solves the problem in a way, in a sort of constraint refinement way, that you add more and more constraints until you actually get a solution. And at that point, in that world, at some point, you have to impose integrality constraints, and we would do that sort of in a lazy way. But that's very much ongoing work, but that's definitely a direction we're taking. So the answer is yes, but it doesn't seem to pay off competition. Okay, so in this approach, what I'm doing now is I'm saying, please give me a heuristic. I'm going to tell you which shape it should have, what the mathematical shape should be. Let's think about polynomials. Actually, this will be very much like a polynomial. So let's think of your state variables as variables in a polynomial. Please give me a heuristic function that is some kind of polynomial of bounded degree, let's say degree 3 or something like that, to keep things computationally limited. But you get to freely decide all the coefficients. You get to pick the polynomial. Give me the best possible polynomial that is a lower bound function for this problem. And I'm saying polynomial as an analogy, but that way, right? Like fit in a way a family of functions in the best possible way. Best possible means we want heuristic values to be high, but it should remain a lower bound. And also have this triangle inequality. And that's what we do. So this is what it looks like. We call this potential heuristics. So the heuristic value of a state is a weighted sum over indicator functions. So we give the computer, we select a set of features. Feature is something that is true or not in a state. For example, in the simplest case, a feature is simply a test that a certain variable is true, if you think of a Boolean representation. It could also be, or in the slide and tile puzzle, it would be like, is this tile at this position? Yes or no? But a feature could also be a conjunction, like is this tile at this position and this tile at this position? So these are the kinds of features we're looking at. If you allow these features to be arbitrary, a single state could be a feature, and then you can always fit a perfect heuristic, because what are we doing with the features? Well, we're combining them as a linear combination. So I go over all my features, I evaluate this indicator function. So is this true or not in this state? So this will give me 0 or 1. And if it's true, I multiply it with a weight, right? So every feature has a weight. The heuristic value of a state is the sum of the weights of the features that are true in that state. And our division of labor is, we say these are the features. The computer says, okay, these are the weights. And we don't try to be smart about the features. What we normally do is we say all the conjunctions that talk about one variable at a time, or all the conjunctions, well, then they're not really conjunctions. All the conjunctions that talk about at most 2 variables at a time, all the conjunctions that talk about at most 3 variables at a time. And by bounding it in that way, it's going to be a polynomial number of features. That's going to be something we want. And then please find me the weights. So we call that dimension because of the analogy of polynomials. Maybe we should have called it degree, but now we call it dimension. So a potential heuristic of dimension k is one where none of the features needs to refer to more than k state variables at a time. Okay, now we have to make sure that a heuristic is actually admissible and consistent. And the way we do that is, in a sense, to write down these constraints. So for every state, its value should be less or equal to what is called h star, which is the actual distance to the goal. So that should be true for all states. This is admissibility. This is the lower bound condition. And consistency is this triangle inequality that says the heuristic value of a state is always less or equal to the cost of taking one action and then the distance from there. Don't want to explain too much why this is a triangle inequality, but well, nevertheless it is. And in a way, so what we can do, okay, one thing we want to do is, well, this has this dependence on H star, which we don't know. We don't know what the perfect coalitions is of this thing. So instead, we only post this condition for the goal states. And for the goal states, well, we know we're already there. The H star value is 0. Then actually we can write equals 0 rather than less or equal to 0, or well, depends if you want to allow negative values. And the nice thing is, if you have this condition at the top, goal awareness, and the triangle inequality, it actually gives you the more general admissibility condition. So by induction from using the top one and then the bottom one along all the transitions, you actually get this one. Okay. So now this is something that we can actually express as constraints over weight. So if we're looking at a particular state, or if we're looking at a particular state transition, for example, over here, I can plug in the definition of the heuristic value of S. I can plug in the cost of the operator. I can plug in the heuristic value for S prime. And if I'm thinking of a particular state S, a particular state S prime, particular operator, well, the indicator functions, I can evaluate them. They're going to be 0 or 1. The cost is going to be a number. I can plug in this number, right? Hopefully that makes sense. So if I do this, what I'm left with, if you think about it, or if you look at it, really, so these get replaced by zeros and ones. So here we have a sum of weights, and here we have a constant plus a sum of weights. Not the same weights, right? Depending on which features are present. So this is actually a linear constraint on the weights. And similarly, from this goal awareness condition, we get a linear constraint over the weights. Basically, the weights of the features that are true in the goal are not allowed to sum up to more than 0. Okay, so this actually gives me constraints that I can then go and optimize. The issue is it's an exponential number of constraints because I have an exponential number of state transitions. So I'm not going to be able to do that. So the question here is, are there cases where I can solve this, but without sort of in a smart way, basically solving this, the problem that has these exponentially many constraints and sort of figuring out which weights should I use in a way that allows me to do it in a polynomial time in my representation size, which is given by the number of variables I have, the number of operators. And of course, I don't just want one solution, because one solution is set all the weights to 0. Give me the 0 function. That satisfies all this. I want something which is as good as possible. However, I want to be flexible regarding what I consider as good as possible. I want to be able to pick what my objective function is. So our goal is to write down a set of, well, if we have this set of linear constraints, it exactly characterizes the set of heuristics we're allowed to use that are admissible and consistent. And then I can combine it with the linear objective and use that to pick whatever I like. For example, maximize the heuristic value of a particular state. So yeah, can we represent them correctly? The answer is, well, sometimes we can. So we can for dimension 1. And this is not so difficult, and indeed it's equivalent to things that have been done before. In particular, this is, again, almost the Manhattan distance if we apply to this example in the different guys. It's very slightly better, but let's not go into these details. It's also the same as the network flow heuristics that were previously known. But the really interesting thing that was not trivial for us was that we can also do it for dimension 2. So I can write down, well, I can solve these exponentially many constraints with the polynomial computation, have something polynomially sized that characterizes all the admissible and consistent heuristic functions that are linear combinations of atomic things that only talk about 2 variables at a time. And this is as often where it stops. So if I go to 3, can't do that anymore. In particular, even if I give you a heuristic of dimension 3, and I'm just asking you to test if it satisfies this consistency condition or not, that is a co-NP complete problem. And therefore, I can't expect, basically what I have to find is the counterexample that violates the triangle. And that, well, finding the counterexample is NP complete. So validating consistency is co-NP complete. And all this does depend on how we're representing the problem for sure, and but glossing over that, just want to acknowledge this here. And this is the main result at this point. There's a slightly more general result, a fixed parameter tractability result, where we're not looking at all features of a certain dimension, but we can pick the features we like. Then this gives us a kind of dependency graph. And then we have an algorithm that is exponential only in the tree width of this dependency graph. And this generalizes the dimension 2 case, because in the dimension 2 case, we'll always end up with essentially with a disconnected graph, with a graph that has a tree width 0, a graph without edges. And I think that's it. And the idea is to take a well-known algorithm for solving constraint optimization and generalize it so that it doesn't solve a concrete problem, but in a sense, symbolic problem where the weights of the actions are left as variables. And then you can end up with a linear program representation of the solution space that you can optimize them. So wrapping this up, so we have constraint languages as a general formalism to express knowledge of solutions. This allows us to integrate multiple sources of heuristic information, and that, yeah, and in particular, in the last part, we talked about heuristic design as a constraint optimization problem, so solving the whole thing whole scale. There's another connection between the second and the third part as well, but I don't want to go into too much detail there. There's several nice aspects for this. For us, the nicest thing is that it really gives us pretty theory, but there's also practical aspects like this modularity. You can come up with a new source of information. You can just grab it and take it. It's also more easily extensible with sort of outside reasoning approaches as an SMT, like if something like an SMT solver, a multiple theory solver, can talk to us in the form of these operator counting constraints, then we can reason about this information. And we have the separation between the implementer that solves the constraint optimization and the, sort of the planning expert that thinks about the constraints. So lots more to be done there, but at this point I should wrap up. Here are the main collaborators on this. One person that is on the call, and the person that did the bulk of the work here that I want to name specifically is Florian Pomerening on the top right here. And the other people, well, let's name them all, apart from their children. So these are Blei Bonnet, Katz and Domshlak, Florian, like I said, Gabi Röger, Jendrik Seib, and Patrick Hasslum, that were all influential in sort of proving the results we talked about today. And with that, I'm done. Thank you.
So much. Any questions?
There is a second topic when you have one knowledge database, currently you will have. So whatever you think you're the database, so long.
So with these pattern databases in particular, like the word database is, I don't know, it comes from NCAN databases. It's in reality, the thing is a bit simpler maybe than it sounds. It's really just a lookup table that gives us an information for each of the possible abstract states. So for a given concrete state that we want to come and estimate with, it's easy enough to find out where in this table we need to look, and then we can get the information out. So that's simple enough. However, you do have like problems of this kind, certainly, as you increase the space of sort of possible abstractions that you're considering. And this is indeed one of the most challenging things, and one of the things that people have worked on over the last year. So when, for example, like if you don't know which abstractions are good abstractions, which sources are good ones, what you often do is you kind of do it exhaustively. Like you look at all the possible projections to 3 variables. Well, if you have 100 variables, it's going to be like 100 choose 3. So that's going to be what, like 160,000. Yeah, something like that. That's a lot. So you really want to limit it to a smaller range. And you certainly want to limit it to a smaller range if you want to look at larger projections. So one of the challenges there is to figure out what are actually good abstractions. And this is what some of the more advanced ideas that we're trying to work on sort of aim at. So for example, in this approach that tries to connect this to Danzig-Wolff decomposition or Bender's decomposition, one important practical challenge that we don't really have an answer for, but at least we know sort of how it fits into the real problem we want to solve now, is figuring out what could be a subproblem that we're not yet considering that gives us additional information that could help improve what we currently have. So in some sense, it's a constraint generation approach, and you have to figure out, well, what kind of constraint do you want to generate? But I wouldn't say we really have amazing answers to that yet. We have some ideas, some will work somewhat well in some contexts. But it remains a hard problem to solve. What is a good abstraction in the context of other abstractions I already have? The basic problem of what is a good abstraction if I don't have anything yet, for that there are really nice techniques based on counter-example guided abstraction refinement. But this problem of give me another abstraction that improves on these things I already have, I think that remains very much a challenge.
So you focus on the question of giving good distance estimates. And we didn't talk so much about how to use them, but you're saying that this is a star that like once you have distance, is it sort of clear what to do, or there are also other?
For now, yes. For now, you just use them with an A star. If you want to do non-optimal planning, there's a lot more other things you could do. In a way, in the optimal setting, having to prove the optimality restricts you on what you're able to do in certain ways, which can be nice, but also limiting. But yeah, so far what we've been doing is just use A star. However, like the more we integrate all these various aspects of coming up with better abstractions, partitioning costs between them, and so on, the more it seems to be turning into a complete solution algorithm. That, I mean, if you keep this running, at some point it will give you a solution. And the temptation, the aesthetic temptation is great to say, let's forget about heuristic search, let's just do that. And that would be really, really pretty. And we're doing that. In particular, Florian and Gabi on this picture are currently working on this. For now, it doesn't work amazingly well. But yeah, it's definitely something we'd like to do more of.
But you're saying like once you've found the solution, you know it's optimal sort of by how the algorithm works more or less.
When you get an algorithm that reaches the lower bound, no? Is that right?
Well, how? Yeah, well, we don't really know what the optimal solution cost is. So the termination check. Let me think about it. I think with the Danzig-Wolff approach in particular, you have a kind of loop where in every round you have a set of operator costs that and there's some hand waving there because I only have operator counts. I only have the counts, I don't have the order. That's one complication. If I had the order, I can basically test, does it work in the abstractions? If yes, I actually have a solution, an optimal solution. If not, I have a way to refine the problem. And that would actually give me an algorithm that I can think of as anytime cost partitioning algorithm, but also a solution algorithm that will terminate with something optimal. That will find something optimal and also realize it has found something optimal, not just, but it's not. But yeah, I shouldn't wave this sequencing problem away. There's a problem as well, that I only have the numbers, not the order.
I guess my question is a high level question, but I'm just trying to somehow compare like stat-based optimization that is different. Like you could just sometimes you have algorithms that find the solution and then gradually improve it, and then we get the optimum.
Yeah.
There are other algorithms that will work sort of more, sounds a little bit more similar to this in the sense that they will get stronger and stronger lower bounds, and then when you fail to improve your lower bound, that's because you actually found a solution matching that lower bound.
Yes.
And then there are algorithms that sort of have more anytime behavior where you say, like, if you terminate it, then it will give you, well, what I have now is maybe not optimal, but you're not allowing it to run for any longer, so let me give you what I have.
Yeah.
But in planning, do you have anything like this concept, like, okay, here's a crappy plan, but this is what I could find.
Yes.
You will like a minute.
Yes, definitely. So there's like one flavor of planning where people just say, give me a solution. And then maybe I'm going to score you on the quality of the solution, or maybe I'm just going to figure out if you solved it or not. And we work on that too. In the past, there hasn't been that much interaction between the ideas for optimal and like anything goes planning, let's say. But there's also these hybrids, like for example, bounded optimality, where you have to give a guarantee, like I have to be within 1.3 of it. The best approach is here, in some sense, concurrently improve a lower bound to know how good they have to be, and run an anytime algorithm to find better and better solutions. And they have a little interaction between them as well, but it's not a lot fancier than running these two things in parallel. It is a little bit fancier, but not a lot fancier.
Nice. Any other questions? So let's start the speaker again. So then we're taking a break, and let's see those who wish can be back in in 5 to 10 minutes. We'll resume for the second half. So we are now back for the second half, which Malte will do it in a text editor, please.
Yeah, okay. So I thought we'd look a little bit at some of the results I talked about last, in particular the one about finding linear programming representations of the admissible and consistent potential heuristics of dimension 1 and 2. And I'll try to do it sort of in pseudo LaTeX. So a planning task, I'm not giving a full definition because that would take too much time, but hopefully definition / example to make it clear, but let's of course make this interactive. So planning task is given in terms of state variables. We have a finite set. So here's an example. They could be X, Y, Z. They're not Boolean in general. They're finite domain. So for example, X could take on these values. Y can take on these values. Z can take on these values. Right? So this would define a state space with 3 times 4 times 3 possible states. Make sense so far? Okay. Now I'm going to look at a particular restricted form of planning tasks, what is called transition normal form. This is very neat for the thing we want to do. You can generalize beyond that, but maybe not in 25 minutes. So let's consider transition normal form. Now, in transition normal form, there's a few restrictions compared to the more general case that people consider. Actually, let's not write I. Let's write SI for initial state, SG for goal state. Then we have variables and actions. So for state is just an assignment to the variables. I would like a kind of maps to character. I don't have that here. So I just use an arrow, but it could look something like this. Now, in general, we can have more than one goal state. In transition normal form, we only have one goal state. That's one of the restrictions. Not hard to achieve through some kind of compilation. So, for example, a goal could be this particular combination of values. And then we have actions. Again, a finite set. The actions describe compactly the transitions we can take. And each action is given in terms of 3 ingredients, a precondition, an effect, and a cost. Cost is just a number. And preconditions and effects are partial assignments. So let me write it like this. Here, our precondition is that X and Y are both 0. And then with a cost of 4, I can apply the effects. And the effect here is that X becomes 1 and Y becomes 2, right? And this applies independently of what variables the other values have. So in this case, for every Z, that gives me a transition. Does this make sense? Okay, this is how we end up with a compact representation. I can have, let me add one more operator. I might say operator sometimes, action sometimes. They're really meant as synonyms. Now, the second restriction of transition normal form, and this is the really nice one for this, is that in every action, the preconditions and the effects talk about the same variables. So here, the precondition talks about X and Y. Therefore, the effect also talks about X and Y. Here, the precondition talks about Z. Therefore, the effect also talks about Z. That's not, doesn't generally have the case. I can have a precondition on X, but no effect on X, or an effect without precondition. In transition normal form, this is always the case. I can create transition normal form through a compilation very easily. Let's just say that this is okay.
So you're saying this is essentially without loss to generality?
Well, with any kind of compilation, depending on what you do with it, it might have preserved certain properties you want and might not preserve other properties. Okay. Here, if I recall correctly, at least, I'm not losing generality over the more general form of this, where I don't have these restrictions, like arbitrary partial states as goal, arbitrary partial states as preconditions and effects. If I allowed arbitrary formulas as preconditions and effects, that changes the game entirely. Well, effects can't be formulas anyway. They're different things, but arbitrary formulas to represent the transitions, that's a different complexity space.
Yeah, but somehow the restriction that I guess the
Right.
premises and the effect that they should be over the same set of variables, that's not a huge issue.
That's not a restriction.
Okay.
That's just for convenience. Okay, so this is our input. Now we want to come up with a potential heuristic. So just to give an example, here is like, maybe let's write it like this. So this is a potential heuristic of degree 1. So to evaluate it on a state, sorry, I'm not really. So I want to put something like this everywhere. Or people would maybe write it as S of x equals 1. I like the model sign for other things we use later on, so like that. Or maybe this even confuses things more than it helps. But what I'm doing here is to compute the heuristic value in a state. A test of x has a value 1. If yes, it contributes 3 to the heuristic value. A test of y has the value 0. If yes, it contributes -3, and so on. This is degree 1. In degree 2, basically these conditions can talk about well, conjunctions that look at 2 variables. But of course, can also look at only 1. Just adding parentheses here for a little bit of readability. And I can also have a constant term. That would be degree 2. Okay. So what we want to do.
But you always have you would always have a linear progression. So degree
Yes.
is like how many variables the state.
Yes.
You're looking at, not that you would have a degree 2 polynomial.
Well, you can think of this. So if these were propositional, you can think of this as 3 times 3xy, right? And therefore the degree is 2. It never makes sense to have x squared because if it's only 0 and 1, right? So that will all be multi. You can think of this.
You're saying I could pull this out and this is 3 times x s models x times s models.
Exactly.
Fine. Okay.
Yes.
Good point.
Yes. Yes.
Yeah. Okay.
And that's really it. And what we're interested in, like I said, is come up with a good heuristic of this form. And what we're doing is saying, these are the features, what are the weights? And I'm going to consider either the setting where the features are all the degree 1 features. So all the size 1 conjunctions and possibly constant term. So I call this F1, features for degree 1. Or F2, where I allow degree 2. And I'm always including all of them. Of course, maybe not all of them might be necessary, but then I can just set the weight to 0, right? So this involves a selection process. So our goal is, or what we want is that we want the resulting heuristic to be admissible and consistent. And like I said in the talk, this is the same as goal-aware and consistent. So we saw on the slides what this means is that goal-aware, the heuristic value of the goal states has to be, well, in the slides it said less or equal to 0. There's some technical reasons why I didn't say equal to 0. That reason disappears if we only have 1 goal state like we do here. So I'm saying, let's just fix it to 0. And consistent means SG is the single goal state. H of S is less or equal to the cost of the action, I think in the talk I had both operator. For all transitions in the state space from S via action A to S prime. And I think we know how the transitions work, right? The preconditions of A have to be satisfied, and then S prime is S with the variables in the effect changed to match the effect of the action. And okay, so what we can do if we are looking at concrete states or concrete transitions is we can plug in the definition of a potential function, which I should write down in a general form. So the heuristic value of a state is the sum over all the features I'm considering of the weight for that feature multiplied with the indicator function that tests whether that feature holds in the state. Does that make sense? Okay, so I can plug this in here. And for example, for goal-aware, So I plug in specifically SG, so the indicator functions I can then evaluate. They're going to be either 0 or 1. So this just gives me a linear equation. A linear equation over the weights, right? Let's say I have 5 features that are true in the goal state. Then I get the constraint that the sum of weights of these features has to be 0. So that's easy. That's going to be simple to represent. Here, similarly, I get a linear inequality for every transition if I do this naive. So I can plug in S, I can plug in S prime, I can plug in the specific action. And then again, H of S is going to be a sum over weights. I don't know the weights yet, so I evaluate the indicator functions. I do the same for S prime, cost of A is just a number. So I'm going to end up with something that looks like this. Just arbitrarily. Okay, I'm indexing the. I should be indexing with features, not just indexing with numbers, just so that so it could be something like this. And one thing that will often happen that will be important is what you see here is that actually many things cancel on the left-hand side and the right. And our hope is basically that they cancel in a systematic way so that many of these constraints actually end up either being the same constraints or we can somehow combine them in a clever way. Okay, what's sort of the next thing I wanted to say? Yeah, let's maybe go straight into the main part. Okay, so one thing we noticed, so the actions are given explicitly as part of the input, so we can, and we see that we get separate constraints for each action. So we can consider this one action at a time. If we can write down constraints for every action, then we take them together, then we're done. So I can consider like a fixed action. If for a fixed action, I can compactly write down constraints for all S prime connected by that action, then I'm home dry. So consider now a particular action, A, and try to compactly express the linear, the constraints. And so we know from these results that we're not going to be able to do that for degree 3 or higher because of these sort of NP hardish problems that are part of that. But we're going to be able to do it for degree 1 or 2. And so what's the basic idea? So one thing to observe is that now that we've selected an action, there's 2 kinds of variables. There's the variables that occur in the action and the variables that don't occur in the action. So our variables V can be partitioned into the ones that are occurring in the action and the others. So this is a disjoint union. So for example, for this action up here, VA would be XY, and then, well, the other thing would be just Z in this case, because it's a small example. I'm calling this VA for action and VC for context, like the context in which the action is about. So. Okay, and now I'm going to use these VA and VC to partition my features. So I can have 3 types of features. I can have features that only talk about action variables. So the variables of the feature, so the variables that show up in the feature, I hope it's clear what this means, are included in my action variables. For example, for this action here, maybe let's copy the action down. I have a feature that only talks about X, or a feature that only talks about X and Y. So that would be part of VA. I can have features that only talk about the context. So in this case, because I only have one context variable, Z, such a feature can only talk about Z. So that's second case. And then the challenging case is where they overlap. So, well, neither. It's neither fully contained in one nor fully contained in the other. So an example here could be I talk just about X, or here I talk about Z, or here I talk about Y and Z. Or maybe let's make this x and y to make it a little bit more interesting. Okay. So that's okay. Resource classification. I'm skipping over the empty feature. If I'm really talking about the empty feature, it fits into these two. But the empty feature, it's not worrying us. Like the constant term of the function. That's not going to be a worry. So what do we want? We want, okay, now there's one thing that we get from our representation. So what, for a given action A, what do the transitions as AX prime look like? And here we get a very nice thing from transition normal form. So we know what X and Y look like in S, we know what X and Y look like in the successor state, and we know that everything else just stays the way it is. So every transition is of the form, well, I have, let's call this the context part of the state, or the context state. Okay, how do I explain this? So SC are the partial assignments, the partial states that are defined over BC, okay? So an element of that is an assignment to all the context values. And the transitions are going to be, and if I think of these assignments as sets, I mean, they're the kind of functions, and I think of them as set, then the source state of a transition would always consist of some context state, and then the precondition of the action as a partial assignment. And S prime will always be, well, the same context state, and then the effect of the assignment, right? So what I really need to do in order to make sure that this works for all the transitions is I need to look at all the possible SC, I need to look at all the possible context states. So what we want is we want that for all SC, H of S less or equal to the cost of the action, which now is a constant, plus H of S prime. And I'm going to rewrite this. Now I should make sure I'm really looking at my notes. Yeah, okay, let's plug this in next, plug it in one more step. Okay, let's just switch the order because I have it the other way around in my notes. Then I will be less likely to constantly switch back and forth in the following. And yeah, I got capitalization wrong here. Sorry. This is just the definition of S and S prime. And let's apply some arithmetic and subtract. Here, the heuristic values are always finite. I'm not allowing infinite potential functions, so I can subtract. Sometimes you want to generalize that, but let's not do that today. And now I'm going to introduce a name for this difference. So this expression here, let's call that delta of SC. So this is the amount by which the heuristic value changes if I apply this action if the context is SC. Right? Does this make sense? So then if we continue here, clearly I have this. And I'm going to rewrite this as a maximization. If it's true for all of them, well, that's the same as saying it's true for the highest of them. So I now maximize over all SC and SC, the delta SC, and this maximum needs to be less or equal to. Does that make sense? It's true for all, if it's true sort of for the worst. Okay, now we're getting to the interesting part, hopefully. So let's look at this delta of SC. So let's plug in the definition. So I'm summing over all the features, the weight of this weighted sum minus the same thing for the successor state, right? This is just the definition up here. And as you see, of course, it's the same. Well, maybe I can make this clearer. So of course, essentially the same sum with the same weights. So I can plug the difference into the sum. And subtract the two indicator functions. Basically, for every feature, I'm looking how is this indicator function changing as I change the state, and this will contribute to the change of the heuristic. Now, here's where we start looking at different kinds of features. So I have the features in FA. If I have a feature, so those are the features where the variables are completely part of the action. So if I have a feature in FA, this difference here doesn't depend on the context state, because F only talks about the action variables. So really, I can evaluate it like this. And because I'm looking at a particular, well, if I look at a particular feature and a particular action, like I'm doing here, I have a parenthesis too many. This is just a number. This is just 0, -1, or +1. So this is trivial. If I have a feature that is completely contained in the context, so it doesn't talk about the action variables.
Just to check, we want the parentheses around the pre minus m on the previous line.
Oh yes, I removed it. I think it was maybe in the wrong place, and one of them was missing, like this. Yeah. I mean, actually, I don't want the weight here. I want to focus on the other part, but yeah. So just the difference of the indicator functions is -1, 0, or 1. In the whole expression, therefore, I get the weight with possibly, well, I get 0 or I get the weight positively or negative. If I have a context feature, well, then it's not going to depend on the precondition. It's going to depend only on SC. It's not depending on the effect. It's depending only on SC. And well, that's just 0. It cancels out. I'm subtracting something from itself. So basically, the intuition here is I have a feature that depends solely on things that the operator is not touching. Well, then nothing's changing there. And in the case of dimension 1, at this point, we're essentially done, because these are all the possible kinds of features we can have. Because a feature only has one variable, either it's a context variable or it's an action variable. It can't really overlap both because I only have one variable. So if I'm at dimension 1, at this point, I see that, okay, delta of SC is simply a linear combination of weights, right? And it doesn't depend on SC anymore. Because, well, yeah, so this expression is either -1, 0, or +1. This expression is always 0. So what remains is that I have a sum over the weights, but it doesn't depend on the particular context state. Therefore, this maximization here really maximizes over something constant. So I really only have like one particular delta for every operator that I can describe as a linear combination of weights with coefficients +1, -1, 0. And that has to be less or equal to the cost of the action, which is the cost. So one insight we get here is that with dimension 1 and one-dimensional potential functions, the amount by which an action changes the heuristic value is actually independent of the context. It's always the same. But this uses both that we have this dimension 1. It also uses that we have this transition normal. So it's not true if we generalize that. For example, if I unconditionally set x to 3, then the change does depend on the previous value. But I can't do that here, right? I have to say what was the previous value. So this leaves a complicated case that we can only have for dimension 2. And of course, we'd also have it beyond dimension 2, but now I'm focusing on dimension 2. Well, but then I know something about the variables of the feature, namely there's going to be one that comes from the action and one that comes from the context. So how do I, let's try to stick to my notes. So F will be of the form, a certain variable has a certain value. I'm using D for domain, and another value a variable has another value, where v comes from the action variable. Sorry, always the line breaks. Well, let's just disable those. Where VA comes from the action variables and VC comes from context variables. And in this case, I'm now looking at a particular action, so I know what the effect is. Therefore, this condition here is something I can, well, either in the precondition or in the effect, I can evaluate this part, right? I'm testing if a particular variable that is mentioned in the action has a particular value. Maybe let's copy this expression again. So I'm interested in this difference here. So something like this. I hope I close all the, no, I put them in the place. Okay. Now, well, it doesn't necessarily cancel out and I can't fully evaluate it, but I can partially evaluate it. So whether VA equals DA, so whether this action variable has the correct value or not in the precondition or in the effect, well, I can evaluate that, right? If VA occurs in the precondition, so this part here is either true or false, independently of SC. And similarly, this part here that talks about is the value that the feature is interested in for this variable, is this the value that actually shows up in the effect, or is it another value? That is something I can evaluate. So I can partially evaluate these expressions. And so what happens is that they're either true or false. If they're false, then the whole thing becomes zero because the whole conjunction becomes wrong. And if they're true, then I'm left with the other part. So let me maybe write it like this. I have 0 or 1 times, and then the part I can't evaluate without looking at the concrete context. And whether it's 0 or 1, I mean, that's something I check and plug in. Feels I'm doing something wrong. Okay, of course, this doesn't cancel out because one of them might be 0 and one of them might be 1. If they're both 0 or both 1, then I'm fine. The interesting case is where it changes. So the whole thing will end up being something like -1, 0, +1 multiplied by this. Does this still make sense? Somewhat? This is sort of where we're getting to the, I don't know, most the hairiest bit, maybe. Giving it some time to think about it.
There's something confusing with the notation because you seem to be the line -2 and line -3 is exactly the same.
This one?
Yeah.
Yes, this is because they can be independently either 0 or 1. That was confusing me as well. But this one could, it's a confusing, I guess it's confusing notation. So, sorry, no. So you mean these two, right?
Yeah.
Okay, so there's basically 4 cases.
I guess the 0s and 1s are depending on the
Exactly. So maybe the notation with the braces is weird. So what I mean is I have either a 0 or a 1 multiplied by this, and either a 0 or a 1 multiplied by this, but they definitely can be different. And if they're not different, if they're the same, I'm done. The only interesting case is where they're different. Makes more sense now?
Yes.
Okay, and this is meant the same way. Okay, so what have we achieved now? Well, so what was I looking at actually? I was looking at one particular difference here for one specific feature. Now I do this for every feature. I evaluate this whole delta of SC. So it's a sum over all the features, WF. And then in here comes the thing we just look at for every feature. And this will be of the form, well, basically of this form, right? So if I want to check out how does the heuristic value change in a particular context, I go over all the features. And for every feature, I check. Okay, so, well, this is for the features that actually cut across both the action and the context. The other ones are simple. We already dealt with those. So simple stuff that doesn't depend on SC plus something like that. And so I still have the sum where I sort of need to care about the context. But the important part about the sum I have now is that in this sum, I no longer have within individual terms any interactions between multiple variables. So each of these terms here only cares about one variable. Does this make sense? So what we want to do is we want to maximize. So the actual objective was to show that the maximum over all the possible context state of delta is less or equal to the cost. So this is the maximum, just for now copy, over this expression, which is simple stuff. And by simple stuff, I mean, it's just like a linear combination of weights and it doesn't depend on SC. And then plus the sum, well, I can maybe be more explicit and say, this is exactly not all the features, but the ones that cut across the weights and then this stuff between. Now I'm maximizing here over a sum, and each term of the sum only talks about one variable. So what this means is that I can group the terms by the variable they talk about, right? So maybe let's look at a little example, right? F of x, y, z, and let's say x, take values from 0, 1, 2, is some constant term plus, and then 10 if x equals 0, and then minus 5 if x equals 1. And I can have multiple expressions with the same test, but of course, oh, well, maybe I should also have the same coefficient. But then, of course, I can combine them. And then other stuff that talks about x equals 2. And sorry, I don't really have, I also have these weights in here all the time. And really in the features I have, the coefficients won't be 10, minus 5, 85, 7. There will be plus 1, 0, minus 1. It doesn't really matter. Once I group them, they become larger numbers. And then I will have similar things for y and so on. And that means that the maximization can actually be decomposed. So I want to have, so I can write f of x, y, z actually as a constant, and then a function that only depends on x, and a function that only depends on y, and a function that only depends on z. Does it make sense? Because this part here, sorry, this part here only depends on x. And so those will be basically coming from the features where the overlap between the action effects and the feature is x. Other terms will only talk about y, other terms will only talk about z. Well, maximizing over a function like that is very easy. I just maximize each part individually. So basically what I want, the final result.
The next to last line now, the middle equality plus, right?
Mm.
Last line, sorry.
Oh, yes. Sorry, yeah. So max delta, max overall SC, SC delta C. It's really the constant part.
And the fact that you got this very clean and simple, is this where you're using degree
I have degree 3, I can have 2 context variables. So in one feature, right? I'm only interested in the feature that overlap with the actions, otherwise they're not. So the action sort of takes out at least one variable that I can partially evaluate, because if it doesn't, the whole thing cancels out. But if I'm unlucky, it talks about one of them, and if I have 3, then I'm left with 2. And if that happens with all the possible combinations of 2, now I have this nasty interaction. So I have to solve some kind of constraint optimization problem that basically where, well, the different, what are they called? Well, the factors or whatever they're called in the constraint optimization problem talk about 2 variables at a time. And in the general form, that's an NP-complete thing to do.
Where you get some kind of quadratic program.
Yeah, you can also like trivially model like binary constraint satisfaction problems like that. Like we have a reduction. Of course, it's not clear because we're starting from a particular structure that any kind of problem can really arise, but we have a reduction, for example, from 3 colorability for dimension 3. But yeah, exactly. So basically, you max. Well, I don't know. Let's write it like this. And I'm sort of mixing the example. Sorry, x in the domain of x, y in the domain of variable. Mixing a bit general notation and an example, but I think you see what I mean. Now, there's one additional complication here. We're kind of almost where we want to be. So if I wanted to solve this for concrete weights, if the weights were given, and I want to figure out for particular weights, what is the maximum delta I can get, then this is now something I can simply evaluate. But actually, all the time we've been working with these sort of arithmetic terms where the weights are 3 variables, right? So everywhere in here, like 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 fx of x, for example, will be something like this: 1 times this particular weight plus, I don't know, twice this particular weight minus this particular weight. So it will be an expression of this form, where the weights correspond to different features. And I don't want to solve this for particular weights, but I want to come up with a representation of the whole thing as a linear program, so that basically, well, for any weights I plug in, if they satisfy the equations, then it will be in the feasible space, and if not, then. So I need to kind of express this as a linear program. And sort of the rough idea, and maybe we shouldn't go into details because of the advanced time, is that we introduce new variables. What do they call them? Yeah, I wonder into how much detail I really want to go. But basically, we introduce new variables. Let's call them delta x. So let's assume in a linear program I could write something like this. Oops. Sorry, copied the wrong stuff. Let's assume in a linear program I had a maximization operation. I can say this variable equals the maximum of these linear terms. Then I can basically replace the max delta SC that I want with constant part plus delta x plus delta y plus blah, blah, blah. And this has to be less than the cost of the action. And that is the thing I want. This is the constraint that describes what has to be true about my feature weights in order for the heuristic to be consistent. Now, the only remaining challenge is this part, but it's not really a challenge. So let's think about it, maybe with an example. So this could be one expression. This could be another expression. And maybe this is the last one. So how do I do this the right way? Well, okay, it's the maximum. So I'm going, it has to be greater or equal to each of the things I'm maximizing over. Okay, where did I copy? These are linear inequalities, but I haven't expressed now that delta x is the maximum, right? What I'm expressing is that delta x is the maximum or more. However, I don't really care about the value of delta x in my optimization. I just care that the variables I actually care about, the weights, if I project to those, I get the right solutions. So what I care about is whether there exists a delta x that will make the constraints come true. Now, the only, apart from like this here, like the things I just introduced, the only location where we're using delta x is in this constraint here, right? So if we set delta x to the maximum, the constraint is satisfied, which is great, which is what we want. If we set it to something larger, we're in a way doing something we don't want to model. So the risk we can run is that we are somehow allowing something we shouldn't be allowing. But setting it to something larger is never going to be helpful, right? It's just going to make the constraint tighter. It's working against us. We never have an incentive to set delta x higher than we want it to be. And therefore, we can simply ignore this. Or another way of putting this is rather than saying, I want the maximum here, I can just as well allow choosing a value which is at least the maximum. And that doesn't really change the feasible space of the LP in terms of the weight variables. Therefore, this maximization is something we can do. And this is because, well, I mean, this is, I think, more as a standard trick in linear programming. You have to be careful. It sort of always works in one direction, not in the other. So with the minimization, we couldn't do it because that wouldn't jive well with the less or equal that we have, right? And maximization works with the less or equal. Minimization would work with greater or equal. Or, well, of course, it also depends on the sign of the coefficients of the and that's basically it. So what we need to do, the set of linear constraints that we have are basically going to be these. And this one. And yeah, I think that's basically it. So of these, where do these come from? Well, the delta x we have to maximize over the different choices we have in the domain of x. So if x has 3 different values, we will have 3 different expressions to consider here. Therefore, we will have one constraint like this for every value of every variable. So the number of constraints that we have per operator is one constraint for every variable and every value. And then like this overall constraint, where is it? This one for every operator. Well, of course, the constraints themselves can also talk about quite a large number of weights. But in any case, what we really care about here is that it's polynomially sized. I can maybe very loosely bound it as something cubic in the input size because the number of variable value combinations that's linear in the input size where we represent the input. The number of operators is linear. And the size of these terms is also going to be linear. So this is where the 3 n's come from. And maybe I can bound it a bit more conservatively by saying, I don't know, that these terms don't become too large or things like that. But this is roughly what we're going to get. And so in some sense, the idea here is, and I don't know how much background you have in these kinds of constraint optimization things. In some sense, it's the idea of marginalization. Like we want to figure out what is the contribution of every variable to the overall sum, and here it factors nicely. Now, if it doesn't factor nicely, but the overlap is somehow bounded, like there's loose overlap, we can still do the same kind of thing, except we need to look at combinations of values. And this is where these tree width bucket elimination kind of results come from. It's the same idea generalized to the case where there is interaction between the variables, but you can somehow decompose it with the tree decomposition. And the tree decomposition is, well, over a graph. Well, for every operator, for every action, we get a different graph. And the graph has an edge for all the, well, for all the features in the overlap. You will have a node for the variables that are the context variables. So if the operator talks about X and the feature talks about X, Y, Z, you'll have a node for Y, Z, and so on. And then two edges will be connected if they share a variable, because then you can't separate them out. And over this graph, you have then to do a tree decomposition. And then, yeah, you'll only be, the size of your linear program will only be exponential in the tree with that tree decomposition. And in our case, because the context variables, because the overlap of the features that talk about action variables with context variables is always a singleton, this graph will have no edges at all. And therefore it's particularly simple. Yes.
So, all of that is going to have number of the action.
Yes, exactly. Yes. Because the action variables we can always partially evaluate, so they disappear. Yes, yes, yes.
This is another, I'm not sure whether this question is even well posed, but I mean, we're trying to solve a piece-based problem.
Mm-hmm.
And so we expect this to be really, really hard.
Mm-hmm.
And then in this, when we're doing this estimates, we say we don't want degree 3 because then we get something quadratic, which is anti-hard. And I guess one thing we say, hey, you're already trying to solve piece-based, so go with quadratic and see what happens.
Yeah.
But there's somehow a reason why I guess then, but then you really want to have guarantees that this computation will run faster. It's rather like, no, I don't even have a good algorithm to solve this if I get this quadratic term. Like, that's a question.
No, sure. I mean, the question is why do we want to insist on solving a tractable problem if we're using it to solve an intractable problem?
Yeah.
And the answer is sometimes you definitely happy to do something intractable at this point as well. And if we, so in some sense we were happy about this result because we knew that with dimension 2, like there's evidence that this is already pretty good. Like you can get good estimates out of dimension 2, a lot better than dimension 3. We don't really know how much better it would be. There's one paper that looks at it, but I wouldn't say it's completely conclusive. And also, I mean, unfortunately, it's polynomial, but it's often nevertheless large already for dimension 2. So if you make it harder, it's going to be worse. But nevertheless, I mean, sometimes it's justifiable, certainly in these kinds of computations, to do something in here. So, for example, like all the topics I talked about today, it's not so obvious from the way I presented it, but they're all closely connected. And in cost partitioning, for example, one of the approaches before the optimal cost partitioning, this canonical heuristic involves writing a similar kind of graph and then computing all the maximum cliques of this graph and doing something with all the maximum cliques of this graph. So this can definitely be exponentially large. So maximum with regard to set inclusion. But we do it anyway. Like no one ever proposed anything more approximate for that. It's just at that point we said, or people said it was, yeah, I guess we were involved in the original paper, it was primarily Patrick Custom. Okay, yeah, at this point we just pay that price. So I think you have to look at the individual cases, sort of see actually how large are these problems you're solving, not just are they NP hard or not, and can you afford to do something very expensive at this point or not. And I think in this general space, there's definitely scope for trying to do NP-hard optimizations of things like this. So we have one paper recently that talks about synthesizing potential heuristics that not for optimal search, but for non-optimal search, where because you're using different algorithms, you don't care so much about admissibility and consistency. Instead, people often do like a greedy search where you just look at the distance estimates, nothing else. And then the property you like best is that your search space has no local minimum. And then you can just go directly towards the goal. And so we try to phrase this as an optimization problem. And is the sigma P2 complete optimization problem, essentially, for the cases we looked at. Like, does there exist a function with these properties? And it's something, I mean, so far we didn't like do anything with it computationally, but I would say sigma P2, that's something we can try. That's not like beyond the realm of what is reasonable, especially like you say, as we're solving a piece-based complete problem to start with. But this can be a bit misleading because the only planning problems where piece-based completeness really materializes are ones that have really, really long solutions. If there's like a polynomial bound on solution length, you're an NP because you can guess and verify the solution. So they tend to be a bit degenerate. So in many cases, it's more like an NP kind of problem, or if for optimality, because the hard part is usually proving the lower bound, it's more like a co-NP style problem. Like there doesn't exist a shorter solution, but I'm often not interested, or often it's easy to see I don't need to care about really, really long solutions. So this is more a co-NP style problem. And this is also, I think, why optimal planning, okay, maybe this is harder to justify. So SAT, in my experience, NP tends to be worse than co-NP. SAT maybe doesn't bear this out because SAT solvers are pretty good at unsolvability, but for many problems, like the NP part with the short certificates and so on tends to scale better than the co-NP stuff. And
I think you could also say, like, I mean, in some sense, the planning problems that you solve, they're probably not, if they somehow captured the essence of piece-based, then maybe you would be dead anyway.
Yes.
And then, so you should be cautious when throwing in extra unrelated NP problems, because maybe accidentally that happens to be a hard problem.
Yes.
And then you fail for no good reason because, like, you're trying to solve a sub-problem and very hard.
Exactly. Exactly. But I should definitely stress that, like, the complexity, is this polynomial or not, this is not like the end of the discussion when it comes to practical use.
Other questions, comments? Otherwise, thank you so much.
Okay, thank you.